Okay, it's got its own logo now. All right, so carboxylic acid, speed run. First and foremost, carboxylic acids are acids. They dissociate in aqueous solution to lose the H plus ion. Of course, they are weak acids, so they only partially dissociate. So they will all have Ka values or pKa values. Because they're acids, they will react with the standard bunch of things that acids react with, like metals, like metal hydroxides, like carbonates. Metals and acids make
Salts and hydrogens.
salt and hydrogens.
Well, hydrogen gas. Sorry, internet.
Acid and base makes salt and water, plus some balancing numbers somewhere. Work it out. Acid and carbonate makes salt, water, carbon dioxide. Okay. With some balancing numbers. If you're writing, let's just do it both ways. If you're writing the formula for the salt, you can either do it with no charges or with both charges, but not just one charge, please. That would be wrong. So either COO minus Na plus or just COO Na, but never with a covalent bond between the oxygen and the sodium. The other thing is that adding a carbonate to an acid is going to be our standard test for carbonate. Standard test for carbonates. Standard test for carbonates it is. But it's also going to be our standard test for acids. Remember that all tests can work in both directions. So if I can use an acids test for carbonates, I can use a carbonate to test for acids. Okay. So yeah, if we add sodium carbonate or sodium carbonate solution to an unknown organic compound and we get bubbles of gas, which we could test to see it's carbon dioxide if we wanted, then yeah, we know it's a carboxylic acid. A bit of naming. Just remember when you're naming that we need to include both carbons there, and we name all carboxylic acids and carboxylic acid derivatives as propan, ethan, butan, methan, whatever it is. And then the next bit of the name, the oic acid, in this case, gives us the exact functional group. But all of the carboxylic acid derivatives, so if I put a chloride on there instead, it would still be ethan and then oil chloride. Okay, if I made it a NH2, then it's ethan amide. Okay, but notice the ethanoic anhydride, ethanoate, it's always ethan. Okay, for all of the carboxylic acid derivatives, all use that naming system. Oh, I'll just say one more thing about diacids, especially, what am I doing there? COOH, there we go. What's happened to my angles? If you've got two acid groups in the molecule, then when we name it, we remember to, James Bond says, add an E. So ethane dioic acid. Di has an E in it. Ethane dioic acid comes up, of course, in transition metals. You've just done it. Why is it important in transition metals? Because it's a bidentate ligand. Good. It's nice to have these links across the topics. Okay. So, moving on to esters. So that one of the more significant reactions that we discuss in the reactions of carboxylic acids is making an ester, and that involves removing water. Hello. And making our new ester functional group. There's the ester there. So an ester is like a carboxylic acid, but instead of the O linking to an H, it now links to another carbon group. Hello.
So a good note for the dioic acids is that it halves the ratio of the moles as well. You know, like when you're neutralizing.
Ah, yeah. So, yeah, if you if we added sodium hydroxide to that, we'd need 2 moles of sodium hydroxide, definitely, and we'd make what? You tell me. What's that called? Sodium ethane dioate. Exactly right. Yeah. So for naming our esters, the carboxylic acid bit, the ethanoic acid becomes ethanoate. So the O8 bit is the extra naming that we use for the ester, just like amide or oil chloride. It's still ethan. And then the methyl group is the alcohol bit that we've added onto the end of the ester. So it's always the alcohol part named first, methyl ethanoate there. And we can have diesters as well, and we can have cyclic esters, which I'll just mention because they'll become important later. So if I had a long molecule with an OH on one end and an acid group on the other end, it can react.
So you know the ethanol chloride, ethan amide. How come the ethan's not ethan ethanol amide? Because they're the same thing, isn't it? It's how the chlorine sort out there.
Sorry, I've lost your question.
Why isn't the ethanol like the ethan and the second one not ethanol? Ethanol as well.
I'm a bit confused about what your question is. Think about that CH3CO is named ethan, and the other bit, in this case chlorine, determines the other part of the name. If we just called it ethan chloride, it would sound very similar to, I don't know, ethyl chloride or chloroethane. It could be easily confused. So we add the oil bit to distinguish that it's an acid chloride. Okay, we don't really need that with amide because it's not going to confuse us. I mean, there's plenty of room for confusion with all chemistry, but so if I make an ester out of my hydroxy carboxylic acid, well, incidentally, what would this be called? Yeah, so the bit I'm hearing there is the 4-hydroxy. That's the important bit. So 4-hydroxy butanoic acid because the acid is always the most important functional group in the molecule. So that defaults to being carbon 1, which means down the end it's carbon 4. So 4-hydroxybutanoic acid. So if I made that into an ester, it would actually react with itself. We'd end up with this 5-membered ring where the carboxylic acid is now part of that ring by reacting with itself. And of course we lose water. Just staying with the water bit for a moment, we use that to drive the reaction because all of these are esterification reactions. They're actually reversible reactions and they're quite slow. So we drive it by removing the water. That, according to Le Chatelier, tips the equilibrium in favour of the products, shifts the equilibrium towards the products because we're removing the water. It's trying to make up for the lost water. How do we do that? What's our reagent that removes water? Make sure you get the conc on the front. Concentrated H2SO4. Yeah, that's a dehydrating agent. And it also can be used as a catalyst, so we can go back and reclaim it afterwards. So the concentrated sulfuric acid takes out the water and drives the equilibrium forward. Okay, so esters are commonly used compounds for what? Sorry, I've just got to. Yeah, so food flavors or smells. They're used in perfumes a lot. And plasticizers, so larger ester molecules get used in the making of plastics. They sneak in between the layers and stop the layers from forming too strong intermolecular forces and therefore keep it flexible. Okay. The other important ester that we need to know about, that's clever, is fats and oils. So I'll just spell this out a little bit. Fat and oil molecules, they're the same type of things, just oils are liquids at room temperature and fats are solids. But fats and oils all have this same backbone, which comes from the molecule glycerol, and then they form a triester at each of the three oxygens there. So we've got the alcohol bit on this side and the acid bit on that side now. And then usually a long carbon chain. I'm just going to use the one that came up in our the thing we did. So typically it's a long chain of carbons. Gone for 17 here, and they don't all have to be the same group. In nature, they almost certainly wouldn't be. And this long chain of carbons can be saturated or unsaturated, which means exactly the same thing as it means in chemistry. I mean, this is chemistry. I mean, when we talk about saturated and unsaturated fats, we mean saturated fats have very, very few carbon-carbon double bonds. Unsaturated fats have more carbon-carbon double bonds. Polyunsaturated fats have many carbon-carbon double bonds. Okay, did you have a question? No? You have that sort of questioning face. No? Okay.
How would you know, because you said saturated has less and unsaturated has more, how do you know when the saturated is enough?
Right, so strictly speaking, saturated means absolutely no carbon-carbon double bonds whatsoever. actually, if you look at fats that we refer to as saturated, like butter or coconut oil, they're a massive mixture, because this isn't nature we're talking about. It doesn't just produce one single product like aspirin or paracetamol or something. It produces, there's probably hundreds of different fats and oils mixed into butter. Most of those will have only carbon-carbon single bonds. Yeah. So that's what when we talk about asaturated fat. But actually, if you look at what sunflower oil contains, it has a little bit of saturated, and it has lots of unsaturated and lots of polyunsaturated. So we talk about sunflower oil as being an unsaturated fat, but actually the picture is very mixed. But in sunflower oil, they are more unsaturated than in butter. Okay, so that's why I'm using a sort of relative term. But as long as you have the understanding of those words correctly in your mind, you shouldn't go too wrong. Okay, so because our oils and fats are made of esters, we can react them in the sort of the reverse reaction of the esterification reaction. We can break the ester bonds apart, and that reaction is called hydrolysis. So hydrolysis is any kind of bond breaking reaction involving water. Now, if we stick some fat in water, not a lot's going to happen. Fats are not soluble in water, so we need something with a bit more pep. So we generally would use fairly concentrated sodium hydroxide for this. You can have acid hydrolysis as well. You will need to boil the fat up with sodium hydroxide probably for hours, is how they would do this industrially. Or you could boil it with HCl for hours. So you can have acid hydrolysis or base hydrolysis. And that will effectively break all of the ester bonds there. So we'll end up with this kind of root molecule. Just going to draw it out. Which the biologists will call glycerol, but we as IUPAC chemists need to call
Propane 1,2,3 trial.
propane. Di has an E in it, but so does tri. 2, 3, triol. Okay. And we'll make, well, in this case, I'll make 2 lots of C17H31. Yeah, that's right. COO Na plus, and 1 lot of C17H33 COO minus Na plus. Okay, so our product here is used to make, or is actually soap. So this is our soap. So our soap molecules are very long carbon chains. You can imagine our sort of long carbon chain here. And then on the end, you've got a polar group, the acid salt group. So we've got a non-polar tail and a polar head, sometimes called hydrophilic. The non-polar tail will stick to other oils and greases, and the polar head will stick to water. So we can use that as an emulsifier, most usefully for washing, which is the industry based on fats and oils. Of course, originally we probably would have used, I'm not going to rub that off. Probably would have used whale oil, but now in more enlightened times we know we can grow our oils from plants. So that's soap making there. If I adjust the conditions just ever so slightly, I'm going to keep the sodium hydroxide. I don't actually need to heat it. And I'm going to add to the reaction methanol we still get the glycerol, but instead of making the soap now over here, we'll now have the methyl ester of the long chain carboxylic acids, the fatty acids they're sometimes called. So the methyl ester of our acids, which is used as biodiesel. Try not to get those two mixed up. They are commonly mixed up. The biodiesel and the soap, that is. Okay, so the only difference is I add methanol for biodiesel. I make the methyl ester for biodiesel. But in both cases, we make the glycerol. Yeah. How are we doing? Loads of time. So, the type of reaction we're talking about here is it's called a condensation reaction. You could call it esterification as well, but a condensation reaction is any reaction where we take two largish molecules, they're not that large, are they? But we take two largish molecules and we condense them slightly, we squash them together, remove a small molecule, in this case water, and we make our new molecule, which is slightly smaller than those two molecules put together. You understand that. So it's become slightly condensed. I don't actually know if that's why it's called the condensation reaction. That's just a guess. I used to think it was called the condensation reaction because, water forms condensation. I don't think that's true either. I just made that up. But either way, that's what it's called. The reaction with ethanoic acid is rather slow. As I said, it's actually a reversible reaction. You have to add conch sulfuric acid to persuade it to go to the right. Even then, you'd need to reflux it for a good half an hour to get any product at all, really, and even then it probably wouldn't be great. So a better way of doing things is to add or replace the OH for a chlorine. So that gives us our first carboxylic acid derivative, the so-called acid chloride. We could have acid bromides and acid iodides as well, but chloride is the one that's usually used. And then we'll get an almost identical reaction, except in this case the small molecule that we would lose will be HCl. And this reaction occurs far more readily. It'll occur at room temperature, pretty much instantly, pretty much 100% product. It can go so completely that we'll actually see little puffs, little clouds of HCl misty fumes appearing above the reaction because the HCl is produced so quickly, it's got nowhere to go. So we need to know the mechanism for this, the so-called addition elimination mechanism. And just going to move that hydrogen there slightly out of the way. The way this goes is the lone pair of electrons on the oxygen there is attracted to the very delta plus carbon. It's got two electronegative groups, the oxygen and the chlorine, withdrawing electrons. So that's going to pull in the lone pair of electrons. And the addition part of that is for the electrons to hop onto the oxygen, breaking that double bond. Addition's always about breaking double bonds. we still have the chlorine. So that would give us that. The second stage in the mechanism is the pair of electrons on that oxygen come back to reclaim their double bond, and at the same time the chlorine gets kicked out. And in addition to that, the oxygen-hydrogen breaks with the electrons going to the oxygen, because it's O+, it needs electrons back. And so, hey presto, we have our product. And we can see how the HCl could get produced by the H+ left over and the Cl- that's been removed. So that's the addition stage at the beginning, breaking the double bond, and the elimination stage, making a double bond and removing the chlorine. But we don't just have to do that reaction with alcohols, we can do it with just water. If we use water, then our product is just a very simple ethanoic acid. But in this case, because we see quite a lot of HCl produced quite readily, this works as a good chemical test for acid chlorides. It's not a particularly useful reaction, but it's a good chemical test for acid chloride. So we just add a couple of drops of water to the unknown chemical. We'll see our puffs of white misty fumes appearing. And we know it's an acid chloride. Of course, it's also quite a strong acid. If I added my water and then I tested the mixture for, its pH, well, I've got ethanoic acid, I've got HCl, and probably some leftover acid chloride as well. It's going to be strongly acidic.
How's the chlorine on the right, the carbon at the start, and then on the bottom, the carbon in the middle?
It's moved out of the way. Does that bother you? Better now? Okay. Got a bit of a kink in my curly arrow there. All right. Just as we can use a small molecule like water, we could use a different small molecule like ammonia. Everything's the same, all the curly arrows are the same. There's just an extra hydrogen in the picture, and then that would lead to our fourth functional group in this series. So we've had carboxylic acids and esters and acid chlorides. Now we're adding to that the amide, that's ethanamide, of course. We still get the HCl produced. And if I go one step further, rather than just adding ammonia, if I add an amine, say I put a carbon group on there, well then that carbon group would follow through all the way to the end there. Still an amide, it's now a secondary amide because our nitrogen is attached to two carbons, and it will be called N-ethyl. So we say N-ethyl because the ethyl group is attached to the nitrogen. So capital N for nitrogen, and then ethanamide at the end. And if we wanted, we could go even further. I could have another ethyl group up there, so adding a secondary amine. And that will be called N diethylethanamide. Right. Nearly there. We'll come back to acylation in the next topic as well, but the acyl group is the CH3CO group, CO double bond. So you'll notice that ethanoic acid, ethanamide, ethanol chloride, ethanoate, all of those compounds have the acyl group in there somewhere. Should really be called the ethan group, shouldn't it? We can add the acyl group by using ethanoic acid. We've also mentioned how we can use ethanol chloride, but there's a third option which introduces the last functional group for this topic of acid derivatives, which is that fella, which is ethanoic anhydride. So the anhydride is a sort of weird symmetrical molecule about an oxygen there with two carbonyl groups or two acyl groups either side of an oxygen. And it's a very good way of adding an acyl group. So when we look at the pros and cons of using these three different reagents for adding an acyl group, what are some of the, let's start over here actually, what are some of the benefits of using an acid chloride? I just mentioned a couple already. Fast. Yeah, doesn't hang around in equilibrium. No catalyst required. So one more.
It reacts readily, so it doesn't, as it just takes place at room temperature, you don't need to heat it as well.
Room temperature, yes. Yeah, so we've got a fast reaction that happens at room temperature without any catalyst, so it seems like a bit of a no-brainer compared with our acid chloride, which is slow, needs heating, and it needs sulfuric acid to make it go. But ethanol chloride has its downsides as well. What are those? Expensive, thank you. Produces HCl, which, you know, in a lab situation makes it a useful chemical test, but in an industrial situation, large quantities of HCl clouds, not good.
Reacts with moisture in the air.
Yes, so it's hard to store, reacts with moisture in the air, as you say. So, and it, you know, it means it goes off easily. If you've got your drums of ethanol chloride, you don't want to leave them around.
HCl is toxic and corrosive.
Okay. So we have clouds of, you know, if we had some sort of spill or vent of HCl, that could, you know, wipe out large sections of the nearby population. It's very exothermic, which again in a laboratory situation isn't an issue, but in an industrial situation we don't want hot reactions getting out of control. Again, that tends to lead to explosions. If the cooling system malfunctions, the pump fails, you know, that's when bad things happen. So although acid chlorides do seem great at first, they also have a lot of downsides. So step in the acid anhydride. So they don't have the dangers of the acid chlorides. So if I sort of compared the acid anhydride with these cons, they are a lot less dangerous, no toxic or corrosive byproducts. Don't have that hugely exothermic reaction. But if I compare them with acids, well, they are still faster than reacting with a carboxylic acid, and there's still no catalyst required. So yeah, that kind of Goldilocks moment in the middle there, where it's not too fast, not too slow, just right. Did I miss anything? I mean, we haven't recapped the whole acids and bases topic, but
The use of ethanoic anhydride will also produce methanoic acid, which can be recycled.
oh yeah, thank you. Yeah,
as these isolating agents.
yeah. So thanks for that. Yeah, the byproduct is ethanoic acid. Once I've taken off my acyl group, if I remove that bit, the bit that's left makes ethanoic acid, which can be reused or recycled. Lovely.
One,
Thank you.
the byproduct of using ethanoic acid is water.
Which is pretty benign.
Yeah.
Don't think anyone's going to be very offended by that. Yeah. Okay. Great. That's fine. Should do that again sometime.